Good morning everyone. Here in this lecture, as the continuation of the previous one, I'm going to explain another problem where we will find out the Bode magnitude plot. So rules for the construction of the Bode magnitude plot already I've discussed in the last class, and here you see here is another kind of problem I have taken where you see this is a pole at s is equal to 0. You can find it. There is a pole at s is equal to 0. So definitely this is not a type 0 system, this is a type 1 system, and construction of the Bode magnitude plot for the type 0 system as we already discussed in the previous lectures. Now here this is a first order pole sections, and you see this is a second order factor, so this we call at second order factor. Why this is second order factor? Because once you solve this is s square plus 4s plus 25 is equal to 0, you get two poles, maybe complex pole, maybe real poles, whatever may be the poles, but there are two poles. And you know, for a single pole, already we have discussed the angle contribution is slope contribution is minus 20 dB per decade. Now for a double pole, because this factor contributes a two pole system, so two poles, that means for single pole minus 20 dB per decade, for double pole that means minus 20 dB plus or minus 20 dB, that contributes and as a slope of minus 20 dB per decade. So that is the new concept here. So that means a second order factor in the numerator gives you plus 40 dB per decade, second order factor and the denominator will give you minus 40 dB per decade slope contributions. And another thing is that in case of type 1 system, what is the initial slope contribution? So already we have discussed for the list of type and the slope. For type 1, initial slope will be minus 20 dB per decade. So we know what is this minus 20 dB per decade and how to draw it, and initially what is the slope contributions. So there is no problem. But once you have to draw this slope minus 20 dB per decade initially, so there must have some place, that means the initial magnitude from where this slope will be started, right? So that is the thing what we have to find out. And in our convention we are considering 0.01 radian per second is your initial frequency, and here we have to find out the magnitude in dB. So that is our next procedure. But before going to get this magnitude at omega is equal to 0.01 radian per second, what we have to do? We have to just find out the that is time constant form realization of the transfer functions given, right? So what we are getting, next step is that we will get the time constant form realizations. That means this is your 50 s. So this is not possible to get 1 plus st form because there is a single pole at s is equal to 0. For the structure like s is equal to 0, we will be always having that part which remains at s is equal to 0, means there is no concept of representing this 1 plus st. So this is not possible. So this will remain same. So next thing is that you take for 1 plus s by 4. Now this has been expressed as 1 plus st form. You can just directly view from here. And from the second order part, what is new here, what you have to do, you have to take 1 plus s square like that. So in order to get that, what you have to do, we have to take this 25 out of here, and here you see 1 plus, I will write like 4 by 25 s plus s square plus by 25. So there is no problem in it. And now this is the time constant form from the second order, this is the time constant form for the first order factor, and after simplifications of these values and rearranging, what we will get, this is 0.5 by s into 1 plus s by 4 into 1 plus 4 by 25 s plus s square by 25. So what is the purpose of actually getting this time constant form? Because one, you can express this 1 plus st form, that means t is equal to again 1 by omega, so you get corner frequency. So corner frequency is very much important for drawing the Bode magnitude plot. So to get the corner frequency, this time constant form is essential. Now for this part, 1 plus st, you see 1 plus s by 4, this is your factor. So here you get t is equal to 1 by 4, means omega is equal to 4. So for this factor It is very simple to get the corner frequency as the previous method we have really discussed in the last class. Now see that this is your second order factor. So what is the corner frequency corresponding to this factor? So that is the newer concept here, right? Here you see I can write like this factor can be written like, say, see here, you see this is 1 plus 4 by 25s plus s square by 25, right? Here in the denominator of s square, right, in the denominator of s square factor, that means 25. So this can be expressed like rest of the thing will remain same. So for the this part s by s square by 5 whole square. So that means 1 plus 4 by 25s plus s by 5 whole square, right? So this cannot be 25, this may be like 30. That means you can get root over 30 square. This can be 40. So root over 40 square, this can be expressed like this. So this part is the corner frequency corresponding to this second order factor. So corner frequency for that will be equal to 5 radian per second, right? That is the this part. If this is say like s square by 24, that means root over of 24 squared. So omega will be root over 24 radian per second, right? So this is the procedure to get the corner frequency from the second order factor. Now we will be having some expression, that is calculations, to find out the initial magnitude. Then we will make the table according to our standard procedure to find out the Bode magnitude plot, right? So we get the 1 plus st form is like this. Next step is to get g j omega, that is the sinusoidal transfer functions. That is as simple as that. Just put the value of s is equal to j omega, and you see 1 plus j omega by 4, 1 plus j 4 by 25 omega plus j omega square by 25, right? So this is 0 plus j0, we can write like this to get the magnitude plot very easy. That is, sorry, the magnitude part. So you can write the real part as 0 plus j0 j omega. This is 1 plus j omega by 4. I can write like 1. See, this is j square. J square means minus 1. So 1 minus omega square by 25, because we have to consider the part like a plus minus jb. So any complex quantity, real part and plus minus of imaginary part. So this is real 1, and this omega square and j square means minus 1. So this part becomes omega square by 25. So 1 minus omega square by 25, that is the real part for that factor, right? There is no confusion in it, plus j 4 by 25 omega. So this part contains j, that means this is the imaginary part for this. Now next part, magnitude of g j omega, that is modulus of g j omega. You see root over mod of this is equal to, again I write a square plus b square, that means root over real square plus imaginary square. And you see here root over real square plus imaginary square, that means this will be simple 0.5 as it is. Next this is 0 square plus omega square, so omega square, right? Root over 1 plus omega square by 16, root over 1 minus omega square by 25 squared plus 4 by 25 omega square. So that is the you see their magnitude part, that is modulus of this will give you the magnitude. And once you get the magnitude, that means you have to convert it into decibel. There is dB. So magnitude in dB you will be found out by just taking the log on both sides and multiplication both sides by 20. So 20 log of this will give you the m dB at frequency whatever you require, right? So next, see the term like just taking the logarithm on both sides, you get log of 0.5, and in this denominator all these terms are there, that means all these times will be subtracted, that is minus log of omega, and this root over means 1 plus omega square by 16 to the power half. That means once you take the log of it, it will be just multiplied, and finally we are getting this term. And m in dv, that means 20 log of mod of g omega. So that is your dv. So m dv means just multiply this 20. So 20 log of 0.5 minus 20 log of omega minus you see 10 log of 1 plus omega square by 16 minus 10 log of, so this is 10 log of 1 minus omega square by 25 square, this is plus actually, plus 16 by 625 omega square. It is the expression, right? Now what you have to find out, you have to find out the magnitude of there is gain at omega is equal to 0.01. So that is to be found out. So omega is equal to, just put the value of omega, and you see am will be equal to am dv, that is equal to, just put this value of 0.01. that means all these terms will be near to 0, and we have to consider this part. And you may put these values also, you will very small value you will get after putting this value in calculator, and that value can be calculated. So this is 5 by 10. So that means this 20 log of 5 minus 20 log of 10, that means 20 log of 5, you see this is 20 minus 6, 14. So 14 minus 20, so that is minus 6 dB, right? So that starts from minus 6 dB magnitude. And once this will start, now up to this, whatever the calculations we have made, what is the conclusion we can see? We just draw this rough graph like this. The graph will be like this initially. That means when you put this value in the semilog graph paper, initial value was 0.01. Now in this magnitude the value was minus 6 dB. So you get this initial magnitude. And next thing is that type of the system is important. Here the type is, this is a type 1 system. As this is a type 1 system, so initial magnitude is minus 20 dB per decade, and you know how to draw the minus 20 dB line corresponding to the reference line. So once you draw the reference line, parallel to this line will give you, say this is minus 20 dB per decade. So this part, up to this part we have calculated. Now how far this line will be extended? This is minus 20 dB per decade. How far this will be extended, that will be calculated based on the table. Now we have to make the table, and from the table we have to find out the corner frequency, and corner frequency will tell you and how this the different slopes will be meeting together. So that is the concept of corner frequency, and the slope contribution corresponding to each of the factor will be given in the table, and from the table also you will get the cumulative corner slope, which is the slope by which that particular line will move on, right? So we will make the table next. I have written just the each of the factors which are required. That is the factor for pole or 0, that is that factor is for pole or for 0. For this factor, what is the slope contribution? For this factor, what is the corner frequency, and how this cumulative frequency slope will be calculated, and that will be written just after going through all these discussions, right? Next you see here I can make this table completed. So according to the problem given, what are the factor? First factor s. Next what is the factor? You see this is s plus 4, and another factor was s square plus 4s plus 25, right? So these are the three factors given in this case. So this is the factor s. This is pole, there is no problem, and slope contribution is minus 20 dB per decade. Now see, this is s, that means there is no chance to get this structure like 1 plus st. So there is no corner frequency. That is why this is type 1 system, and initial slope is minus 20 dB per decade, right? So that is the concept. Next part, s plus 4. For s plus 4, what is the corner frequency? 4. We have calculated. What is the corner frequency corresponding to the second order part? 5. we already calculated. Now the thing is that this s plus 4 is again in the for pole, that is for a single pole. That means for this contribution is minus 20 dB per decade. Next, s square plus 4 is plus 25. So this is a double pole factor. So double pole means this is definitely poles. We can write it 2 pole, right? So if there is 2 pole in this factor, so what is the contribution? That is minus 40 dB per decade. So that is the you see the table where this cumulative slope, either you can write it or you can just go on calculating this, drawing this magnitude plot. Now next step, you see this table is required, and based on this table we will have to find out the you see this is the Bode magnitude plot. Now roughly I am doing just I am shifting this table in rightward directions, and some datas we require, and from that we will draw the magnitude plot here. See, this is the the semilog graph paper. You can draw it in semilog graph paper itself. Now this is your 0 dB line. This is plus 20 dB. This is minus. This is plus 40. This is minus 40 dB. And this is our reference sections, right? Say we will take the last decade. This to this is 1 decade. Now say 0 dB to plus 20 dB. So magnitude to this, and if you draw this line, what is the slope? This slope you can write it like this is plus 20 dB per decade. So this is plus 20 dB per decade slope, right? And similarly, if you draw the structure like 0 to minus 20 dB line, so this is your minus 20 dB line, this is your minus 20 dB line. Next you can draw this is line. So this line means minus 40 dB line, and you can draw from 0 to plus 40. So this straight line is having slope of plus 40 dB per dB, right? So these lines are standard lines which are normally you have to draw first. Next, what you have to do, you have to just check the table, right? Here we will see first of all the initial magnitude, that means at omega is equal to 0.01. Now coming to this point, omega is equal to 0.01, what is the magnitude? Minus 6 dB. So this is minus 6 dB. So from this the graph will start, and initial slope is minus, as this is a type 1 system. This is a type 1 system, means initially slope is minus 20 dB per decade. So just take 2 scales to draw the parallel line of this minus 20 dB per decade. So this is minus 20 dB per decade. So from here you will have to draw a line parallel to this line, just parallel to this minus 20 dB per decade, and you may say this 20 dB per decade. So this is the line having slope minus 20 dB per decade, because this line and this line had to be made parallel, right? Now up to which these have to move, that is the question. The next corner frequency, if you just remember the table, there are the corner frequency s plus 4. For s plus 4 factor, corner frequency was 4, and for second order factor this corner frequency was 5. Now the rule is that this has to move up to the corner frequency which is minimum. So out of this 4 and 5, this is your minimum corner frequency, right? This is your minimum corner frequency. So this line, actually the slope is not right. Okay, just draw the slope like just this should be the parallel line. Unless this is parallel, so your graph is not right. So this is your minus 20 dB per decade line, and this goes up to plus 4 dB per decade, because out of these all these corner frequencies available in the table, you see that value 4 is minimum. So for example, this is your 4. So this is omega is equal to 4, that you can get from this graph, and up to this this curve reaches, and once it reaches to this, what it sees again, I see the factor is s plus 4 corner frequency, the factor is s plus 4, and this factor is for pole. For a single pole contribution is minus 20 dB per decade. So initial before this, what is the slope? Minus 20 dB. After this, what should be the slope? Minus 20 dB. So actual cumulative slope which will be minus 20 plus or minus 20, that means minus 40. So minus 20 minus 20, So that is your minus 40 dB per decade. So up to next, that is minus 40 dB per decade. This is the slope. So up to omega is equal to 5. So this goes up to omega is equal to 5. And when it reaches omega is equal to 5, what it says? This is a second order factor. That means at omega is equal to 5, slope contribution is minus 40 dB per decade. So this is your minus 40 dB per decade. So up to this you have reached. Now here you see the slope is minus 40 dB. So minus 40 dB is your previous slope, plus or minus 40 dB is your next contribution due to this second order factor. So what is the resultant slope? That is minus 80 dB per decade. So you need to draw a reference line which is minus 80 dB per decade slope, which contributes minus 80 dB. Minus 80 dB means 40 dB to minus 40 dB. So that means if a line is drawn from this magnitude, so this slope is minus 80 dB per decade, right? So parallel to this line, one slope is to be drawn, right? So you draw a line parallel to this line, and this may extended after this. So this is having slope of minus 80 dB per decade. So this is the, you see, the Bode magnitude plot for the transfer function given. I repeat, first of all, this is the type 1 system. So initial slope is minus 20 dB per decade from the initial magnitude minus 6 dB, and this goes up to the minimum corner frequency from the table. So minimum corner frequency is S. So this goes up to S is equal to, that means omega is equal to 4. Once it reaches 4, it sees this is for a pole. It sees this is for a pole, and for a pole contribution is minus 20 dB per decade for its own contribution. So minus 20 plus of previous slope minus 20 dB, that is your cumulative slope. So the resultant slope will be minus 40 dB per decade. So resultant slope is made parallel to the minus 40 dB per decade line, and this goes up to the next corner frequency. Here there are only two corner frequencies, so we are getting a corner frequency which is 5, and this goes up to 5. Once it reaches 5, it sees this is a second order pole. So once this is a second order pole, it is having slope contribution of minus 40 dB per decade. Once it is having minus 40 dB per decade, it sees the previous slope was minus 40 dB per decade also. So minus 40 plus of minus 40 means minus 80 dB per decade is the slope. And once you get minus 80 dB per decade slope, so this slope starts from omega is equal to 5 and ends anywhere. You can draw this line. So to get this minus 80 dB slope, you have to join plus 40 to minus 40. That means the total magnitude change is 80 dB, and this is downward direction, so that is minus 80 dB per decade slope. So that is the way you can draw for any type, any order, any factor, right, like this. So this is the way how can draw the Bode magnitude plot, right? And you see, the next class we will discuss about the drawing of the Bode phase plot, because in order to get the stability or in order to complete the Bode diagram, you need to have a single graph where corresponding to this frequency axis you will be having Bode magnitude plot on the top of the graph, and next you will be having a Bode phase plot at bottom of the graph, such that for the simultaneously, that means for a single variation, for any variation of the frequency, we'll be getting the variation of the phase as well as the variation of the magnitude, and from that stability can be analyzed, right? Thank you.